Hi, I'm Margie Coleman. Today, we're going to work on generating equations for given roots. First, we need to review the relationship between roots and factors. Here's a function given in factored form. F of x equals the quantity x plus 2 times the quantity x minus 3. Let's graph this function and see what the roots are. So we enter it in our y equals screen by pressing y equals. And we have parentheses x plus 2, so I have my parentheses key here. I use this button for x plus 2, close parentheses, and then I open the second parentheses with x minus 3, and I close that parentheses. And now let's take a look at this graph, and I like to start at the zoom screen and choose number 6, zoom standard, to get a nice normal viewing window. And we can see that it looks like it has two roots. It crosses the x-axis twice. Once here, seems to be at -2, and another time right here seems to be at 3. Now let's go back and compare that to the function itself. You'll notice we found a root at -2, and we had a factor x plus 2. We found a root at 3, and we had a factor x minus 3. This is a pattern that is reliable. Whenever we find a root for a polynomial, there should be a factor that is x minus that value. However, you might have noticed the function when we looked at the graph seemed to be quadratic, but we don't have an x squared anywhere in this function. To put it into its general form, all we have to do is multiply our binomials together, multiply our factors together. So I have x plus 2, and I have x minus 3, and I'm just going to multiply those together. And you may remember the FOIL method, but we're just going to multiply each term in the first parentheses by each term in the second. So I have x times x is x squared. X times -3 is minus 3x. 2 times x is plus 2x. And 2 times -3 is minus 6. Now I can simplify because I have like terms in the middle, -3x and positive 2x. I can add those together, which gives me -1x, which I don't need to write the 1. So my function is x squared minus x minus 6. Now, if I put this function in the calculator, we would expect to see the same graph and the same roots. Let's put that in the graphing calculator and see if that's true. We'll go to our y equals screen. We'll enter our polynomial that we found, x squared minus x minus 6. And again, we'll go to zoom standard number 6. And it does appear to be the same function we had last time, with a root right here at -2 and another one right here at 3. Let's try another example with two roots that are both integers. We want to find a polynomial with roots at 2 and 5. So we'll write the factors and multiply it out and then check with the graph. So if x equals 2 is a root, then that factor would be x minus 2. And if 5 is a root, then I would have a factor x minus 5. Now I'll just multiply that out. X times x is x squared. X times -5 gives me minus 5x. -2 times x gives me minus 2x. -2 times -5 gives me plus 10. Again, we add our like terms in the middle. So I have x squared minus 7x plus 10. And once again, we can verify this by putting the function in the calculator and making sure that the roots are 2 and 5. So let's put this one in the graphing calculator. We'll go to y equals. We'll enter our polynomial, x squared minus 7x plus 10. And again, we'll use zoom standard number 6 to get a nice easy viewing screen. And it seems that we have roots here at 2 and right here at 5. Let's do another example with two roots that are integers. This time we want a polynomial with -3 and 4 as roots. And we'll write the factors, multiply it out, and check with the graph. So if -3 is a root, then the factor is x minus -3. And if 4 is a root, then the factor is x minus 4. Before we multiply this out, we have minus negative, and we usually don't leave things like that. Minus a negative just simply means plus. They cancel each other out. So I have x plus 3 times x minus 4, and we'll multiply. X times x is x squared. X times -4 minus 4x. 3 times x plus 3x. 3 times -4 minus 12. Again, we'll add our like terms. So we get minus x, minus 1x, and we don't need the 1, minus 12. Now let's work with one where we have 3 roots, and they're all integers. So now we'll find a polynomial with roots at -4, 2, and 6. Again, we can write the factors. We'll just have 3 of them, so the multiplication will take a little longer, but it's the same process. So x equals -4 creates a factor x plus 4. X equals 2 creates a factor x minus 2. X equals 6 creates the factor x minus 6. Basically, we're going to use the same multiplication strategies we used before. We're just going to use 2 at a time. So I'm just going to bring down my x plus 4 and deal with it on the next pass. And let's just multiply these two together. So I have x times x is x squared. X times -6 is minus 6x. -2 times x is minus 2x. So that all together would be minus 8x. -2 times -6 is plus 12. Now I have to multiply the x plus 4 times this new trinomial. So I'll take each term in the first parentheses and multiply it by each term in the second. So I start with x times x squared. That's x cubed. X times -8x is minus 8x squared. X times 12 is 12x, plus 12x. Now I'll do 4 times x squared is 4x squared. And we'll do 4 times -8x is minus 32x. And 4 times 12 is plus 48. Now I have all kinds of like terms I got to get together. The easiest thing to do to stay organized is go in order of exponents. So first I want to find every term that has a third power, or x to the third. And we just have 1. So we have x cubed. And I like to just scratch it out and say, okay, I used that one. Now we're going to do all the ones that have a 2 for an exponent. So I have a -8x squared and a positive 4x squared. When I add those together, I get minus 4x squared. So I've used those two. Now we'll go for the x's. I have plus 12x, minus 32x. So that gives me minus 20x. So I've used these two. And all I have left is plus 48. So this function, if I put it into my calculator again and check for roots, I should have roots -4, 2, and 6. And you can try that on your own to verify it. Now let's try one where the roots are irrational. Suppose I want a polynomial whose roots are -1, radical 2, and negative radical 2. We're going to write the factors and multiply just like we did before. So I have x plus 1, x minus radical 2, and x minus negative or plus radical 2. Again, we want to use 2 at a time. I think it's always best when you have radicals in 2 of them to start there. Multiply those first. So I'm just going to copy the x plus 1 and use it on the next time through. So x times x is x squared. X times radical 2 is radical 2x. Negative radical 2 times x is minus radical 2x. So I have radical 2x minus radical 2x, which just equals 0. So that canceled out. And now I just have negative radical 2 times positive radical 2. Negative times positive is negative. And when I multiply a square root by itself, that's square root of 2 times square root of 2 is square root of 4. And the square root of 4 is just 2. In other words, whenever I multiply a square root by itself, it just gives me whatever was inside. Now I can do the final multiplication. X times x squared is x to the third. X times negative 2 is minus 2x. 1 times x squared is plus x squared. 1 times negative 2 is minus 2. And that's fine, but usually mathematicians tend to write polynomials in decreasing order of exponents. So I just like to rewrite things. Put my third term first, my second power term next, so my x squared, then my x term, and then my minus 2. So x cubed plus x squared minus 2x minus 2 is the polynomial that has roots at negative 1, radical 2, and negative radical 2. And again, you can use your calculator to verify that. What happens when 0 is a root for the polynomial? Let's find a polynomial with roots at 0, negative 1, and 1. Again, we'll write the factors and multiply. So x equals 0 means I'd have a root that looked like x minus 0. And then, of course, negative 1 gives me x plus 1. And 1 gives me x minus 1. However, x minus 0 seems like we're writing a whole lot of stuff just to say x. Because when I subtract 0 from something, I'm left with whatever I started with. So I don't need to write this as x minus 0. I can just write x by itself in front of these two parentheses. The nice thing about that is, clearly this is the piece I'll save till last, and I'll just start with these two together. So x times x is x squared. X times minus 1 is negative x. X times 1 is positive x. Minus x plus x is 0. So again, those outer and inner terms canceled, and I have 1 times negative 1 is minus 1. So for a last step, all I have to do now is distribute my x. So x times x squared is x to the third, and x times negative 1 is minus x. So the polynomial x cubed minus x should have roots at 0, negative 1, and 1. And again, you can verify that on your calculator. Now let's work with fractions as our roots. What if I want to find a polynomial with roots at 0, negative 2, and 3/4? Let's write those factors and multiply. So we said for x minus 0, we're just going to write x. For x equals negative 2, I'm just going to write x plus 2. And for x equals 3/4, I can write x minus 3/4. And I think you can predict that when I'm multiplying this, I'm going to have a lot of fractions that I'm carrying around and working with. So there is a shortcut. I can rewrite this factor. All I need is for this factor to, when I set it equal to 0, to give me the root of 3/4. So if I think about it, x minus 3/4 equals 0. If I multiply through by 4 right now, I get 4x minus 3 equals, and 0 times 4 is still 0. And 4x minus 3 is a lot friendlier looking factor than x minus 3/4. So what we can do whenever we have a fraction is we can convert it this way before we start. So I have x times x plus 2 times 4x minus 3. So I've cleared the fractions before I start, and it saves a little trouble later. So we'll bring down that x, and we'll multiply these two together. X times 4x is 4x squared. X times minus 3 is minus 3x. 2 times 4x is plus 8x. 2 times negative 3 is minus 6. And again, I have some like terms here. Negative 3x plus 8x is 5x, so I have plus 5x minus 6. And now I'll distribute my x. So I get 4x to the third plus 5x squared minus 6x. And again, I can put this polynomial into my calculator to verify that those are the roots. Let's do one final example. Let's find a polynomial with roots at negative 2/3, 1/5, and 2. So for negative 2/3, I get the factor 3x plus 2. For 1/5, I get the factor 5x minus 1. And for 2, I just get the factor x minus 2. Again, I always bring the one out front down to use later. That's just my preference. We'll multiply these two together. 5x times x is 5x squared. 5x times negative 2 is minus 10x. Negative 1 times x is minus x. Negative 1 times negative 2 is plus 2. I have my like terms. Negative 10x minus another x is minus 11x plus 2. Now I have to distribute both of these terms throughout the second parentheses. 3x times 5x squared is 15x to the third. 3x times minus 11x is minus 33x squared. 3x times 2 is plus 6x. 2 times 5x squared is plus 10x squared. 2 times negative 11x is minus 22x. And 2 times 2 is plus 4. And now I'll combine my like terms. So I have 15x cubed. I have a minus 33x squared and a plus 10x squared, so minus 23x squared. I have a 6x minus a 22x, so I'm going to have a negative 16x, and I have a plus 4. And this is the polynomial that should have roots, negative 2/3, 1/5, and 2. In summary, today we talked about creating polynomial equations that have certain given roots. All we had to do is take every root, write a factor using that root, which would just be x minus that value, list all of our factors, multiply them all together, and create a polynomial.